Hi, this is David from the Academic Resource Center, here to talk to you again about Physics40B. And in this video, we'll be talking about the gravitational potential energy equation, which you can see here. So I want to talk about a little bit about where this equation comes from and why it is the way it is. So first off, we can derive it from the equation that you should probably already know, which is Newton's law of gravity, that being g(mm) over r squared. And so you might be familiar with that in these terms. Now we know that work is the integral of force with respect to distance, as you can see here. This is something you should have learned in Physics 40A. So if we integrate that force equation from Newton's law of gravity with respect to distance, in this case using the variable r instead of the generic variable s, we'll get the gravitational potential energy equation. So I'm not going to go into the minutiae of how exactly that works, but that's one way you can look at it. And that's where this negative value comes from, which can be a little confusing because why do we have negative energy here? So we can say that just due to the calculus, when you take the inverse of the power rule here, you'll get a negative sign there. That's not really a satisfying answer to why we would have a negative, because that's just the calculus answer. There's no physical notion behind that. So let's explore that a little bit more. So here I've drawn out a scenario where we have two objects of different mass. One of them is being attracted to the other. Well, they're both being attracted to each other, technically, by the force of gravity. So if we just look at this equation again, if we have some big distance, r again being the distance between their centers of mass, like at state 1 over here, r will be a fairly big number. And when r is big, the total gravitational potential energy is going to be small because we're dividing by that big number. But as we get closer, say to position 2, r becomes a much smaller number, and the gravitational potential energy is higher. So maybe that's also kind of unintuitive. How is it that when we get close to this value here, we have a higher potential energy? Because it feels like it should be the other way around, especially if we consider mgh, what we learned in high school, where h is like the distance between these two things, sort of like r, g is just a constant gravity, and m is the mass of one of them. That's sort of the opposite, because as we can see here, h is now in the numerator, so it has the opposite behavior. All right, so let's keep looking at this. So one of the other ways you could look at this is using the sum of energies, or conservation of energy. So there's nothing being added or removed from the state. So this delta E should remain constant from state 1 to state 2. Our potential energy, or if we start at position 1 with no velocity, our initial kinetic energy will be 0. And as we mentioned, our potential energy, if we just assume this is positive for the moment, is going to be increasing because, again, like we said here, r is big, so the potential energy is really small. And over here, r is small, so the potential energy is large. So if we go with our assumption then that the potential energy is going to be increasing as we go from state 1 to state 2, what about the kinetic energy? Well, we also know that kinetic energy is equal to 1/2 times m times v squared. So regardless of whether v is positive or negative, it's squared, so it'll be a positive value. And again, we'll have an increasing kinetic energy. So if, like we said, the delta E total for this change from state 1 to state 2 is 0, how can we add to both of these and retain this no change in energy? Because we have two positive numbers, you can't get 0 by adding those together. So if we go back and change our assumption to be that potential energy is negative, we will again start with a small negative number here, but we'll be getting more negative as it moves from position 1 to position 2. So again, just because it's in the denominator, that's the change we see. And so if that's the case, then we'll have the opposite, where the magnitude is still increasing, but because of that negative sign, the potential energy itself is decreasing. So now we'll have a negative number and a positive number, and those can, in theory, add to equal 0, no change in potential energy. So that would be, I think, the most satisfying reason as to why the potential energy in this equation is negative, even though, from a more objective standpoint, it might seem like negative energy is a little counterintuitive. This is probably the best reason why. So again, if you have any questions about this, you can reach out to us by email. Those will be in the description of this video, and also with our office hours. Thanks, hope you learned something, and I'll see you again next week.